All right, so let's start with a very easy question and fundamental question, and that is to draw all constitutional isomers resulting from an elimination reaction. And this is not telling you whether it's E1 or E2, so it does not matter. So both you should consider. You simply have to draw all the possible products that can arise from an elimination. In other words, a dehydrohalogenation, removing HX. And so for that, we first need to look at beta hydrogens, and we have two here, and let's just call them 1 and 2. And so if we eliminate H1, we're going to get this alkene right here, and also, sorry, not this, but this trans and the cis, both. Remember that we have two hydrogens, and depending on, I'm going to label 1' and H1 and H1'. And again, this is H2 and H2'. And depending on which one you remove, you're going to get these two isomers. Of course, we understand this is more stable. And if you draw the transition state, you would understand also how the transition state it plays a role. But if we remove H2, then what you would get is you're going to form the double bond between where H2 was and the bromine was. So that's the easiest to draw. And you can, of course, indicate plus cis isomer. And just got to make sure you have your carbons right. 1, 2, 3, 4, 5, 6, 7, 8 carbons. 1, 2, 3, 4, 5, 6, 7, 8 carbons in each starting material and products. And so this is the type of answer that I would be looking for. If you indicate only one isomer, that would be incomplete. You need to either indicate the cis isomer or you draw all together. And if it does not necessarily have to be cis, you can be, if you don't have hydrogens, you don't call it cis or trans, you call it E or Z. And so you have to draw it. Or you can just say plus diastereomers. We understand that these two are diastereomers. A more common word is geometrical isomers. Now, if we want to continue with our second problem, we also have to identify beta hydrogens. And this is just straightforward. Again, let's just label 1 and 2. If we eliminate H1, we're going to form a double bond right there. Everything else remains untouched. Of course, we also get the diastereomer. These two are diastereomers. Trans, cis. And if we eliminate H2, the double bond is going to be in a different position. And in this case, it does not matter. This hydrogen, it's this right here. In this case, it does not matter whether we call it cis or trans because these are identical groups, methyl groups. And so if the question is to draw all constitutional isomers resulting from an elimination, then you should draw all three products in this particular case, and all four products in the case above. Now, in this other case, we do a similar approach. We simply locate beta hydrogens. We call this 1, we call this 2. If we eliminate 1, and we're not talking about right now the transition state or anything like that. We're just trying to see the products that we would get. Ethyl remains there. Now we form a double bond between where 1 was and the chlorine was. This comes from elimination of H1. If we eliminate now H2, now we're going to have a different molecule. And that's what I'm looking from all of you to be able to draw. These two are constitutional isomers. And so that's an easy approach to do it. First of all, you have to locate all beta hydrogens. In this case, no stereochemistry is indicated here for the substituted cyclohexane. And so you don't have to worry about what's antiperiplanar to what or anything like that. You simply assume that you're going to be able to eliminate. And that's the end of the story. Now, that's one type of question. Another type of question would be if you're confronted with something like this, and it's asking you which alkyl halide would give rise to this as the sole product, as the only product. And so for this, you have to be a little bit more judicious. And my approach is, okay, let's see what happens if I start with an halide here, and I'm going to have a beta hydrogen here. So this can eliminate and give rise to this product, no problem. But the problem is that this one can also eliminate and will give rise to a different product. And it's not going to be the only product that we would get. And so this will be an incorrect answer. Now, the one that would give you this and only this would be something like this, in which we only have one possibility for beta hydrogen to be removed. And it's this one right here. This is the beta position, this is the alpha position, beta position, and only this one can kick out this halide. And this will give rise to a single product. And in this case, two hydrogens are identical, so there's no possibility of stereoisomers. So this will be the correct answer for that particular question. Now, for this other question, a similar approach, we draw our skeleton here. Now, we can place the halide either here or here. And let's see what happens. In this particular case, we have a beta hydrogens. We have one right here. We have one right here, and we have one right here. So we can immediately tell, okay, if this gets eliminated, it's fine. Will give us this product. So H1 will give us that. But as soon as we start removing H2, elimination of H2 will give a different product. And so this would not be the correct answer. However, in this other case, now we have only one beta hydrogen. Sorry, it's not that the hydrogen we need to remove, but this one right here. This is not a beta hydrogen. This one is the beta hydrogen. And if we remove this beta hydrogen and this halogen, this will give rise to the exocyclic alkene as the sole product. Ignore this because this is not part of the answer. So it would be the base coming in, taking out, and you form an exocyclic double bond. Okay, so this one right here, if we want this to be the only product, so okay, we have a couple of possibilities. Again, we start by drawing some possibilities here. We want this to be the same. It's a methyl group. So we can have our chlorine atom here or here, and let's see what happens in either case. If we have it here, fine. We can eliminate H1, and it will give rise to this product. But we also have beta hydrogens here. Let's label them as H2. And if we eliminate H2, it will give rise to a different product. And so this is not the answer you should give, because this will give you a mixture of products. In one case, you form a double bond here. In the other case, you form a double bond here, depending on which beta hydrogen you remove. So the correct answer should be based on symmetry. You simply pick the other possibility was here. You put the halogen atom here. Now, these two beta hydrogens are completely identical based on symmetry. Beta hydrogens, each of those will give rise to this as the sole product. Any of the beta hydrogens will give rise to a sole product. And this would be the correct answer. This will be the correct answer. In this case, this will be the correct answer. In this case, this will be the correct answer. Now, let's look at the final one. And in certain cases, you will find that it's not only one structure that can give you the product you want, but several structures. Let's see, for example, this one right here. So I have a methyl here, and then there's a hydrogen. If I eliminate this, H1, this will give rise to that alkene. And that's one correct answer. There's no other beta hydrogen in this case. So this would be one correct answer, but you would be incomplete because there's also another possibility. And the other possibility is if you have this, CH3s, CH3. Now, each of this is also a beta hydrogen, and this will give rise, and they're identical. Each of these are identical, and they will give rise to that as the sole product. Now, if you were to ask me which one would be faster, now you know that tertiary halides are faster for E2. So if I ask you which of the two would give a faster reaction, then you would pick this. But if the question is what alkyl halide, or draw two alkyl halides, or all alkyl halides that would give you this as the sole product, then you have to draw both. And so this is a primary alkyl halide, this is a tertiary. They both give rise to the same product as the only product. The only difference is one reacts faster than the other. Okay, so now the arrow pushing is clear, but let's do one more practice and let's bring in rates now. So we have a reaction of a primary alkyl halide with T-butoxide. This is a tertiary base, alkoxide base. T-butoxide abbreviated. Can be sodium or potassium in T-butanol. So usually this combination, it happens because you have T-butanol. If you mix it with sodium metal, you form sodium T-butoxide plus hydrogen gas. You've probably seen videos of people, they throw sodium in water, they form sodium hydroxide and hydrogen, and you'll see explosions. We obviously don't do that in the lab, we do it more carefully, we never see any explosion, but that's a way to generate sodium T-butoxide in T-butanol. So, okay, so we were talking about an E2 reaction, and it's asking us to show an arrow pushing mechanism and draw all the byproducts. And by byproducts, of course, let's see whether we can get an organic byproduct, and I think we're going to be able to recognize that there's only one beta hydrogen able to be removed, and so we'll give us one as the sole product, organic. This is only one alkene. However, what it means by the other byproducts, we also have T-butanol, because our arrow pushing would go something like this. We take that proton, we form a double bond, and finally we take out the bromide. So T-butanol plus bromide. And if you happen to know which is the countercation for the T-butoxide, let's assume it's sodium, so then it would be sodium bromide. So that takes care of that. And now it's asking us to describe what happens to the reaction rate if we perform some changes. First of all, let's recall for an E2, the rate is equal to the concentration of alkyl halide and the concentration of the base. So it's a bimolecular. Two species are involved in the rate determining step. Okay, so if the solvent is changed to DMF instead of T-butanol, DMF, it's polar aprotic, and this favors E2, so we can say that the rate increases. Now, what about if the concentration of T-butoxide is decreased by 1/3? We know that E2 is involved, the base is involved in the rate determining step, and so if we decrease the base by 1/3, this will result in a decrease in rate by 3 times. So this is important to take into account. If you say that it's decreased by 1/3, it's exactly the same. It decreases 3 times. So just to clarify, if we say that the rate decreases not 3 times, but decreases 1/3 of the original rate. So I think that's more clear or clearer than saying by 3 times. Now, if the base is changed to sodium hydroxide, the basicity is decreased. Therefore, the rate will also decrease. And here we're not being quantitative. We're just saying that basicity is decreased. The rate would decrease, and at the same time, we can start seeing SN2 competitive reactions. In other words, we form the alcohol. Something like this, hydroxide attacking the primary alkyl halide. And we know that SN2 are very good to do in primary alkyl halides like this. And so the rate of E2 will decrease. That's all it's asking here. Now, if the living group is changed to iodide instead of bromide, the rate will increase because iodide is a better living group. Now, a different question is, what happens if you change the halide to this? And so here, the question is asking you, is testing that you're able to transform this structure, this condensed formula, into a structure. And so CH3, CH2, 1, 2, 3 CH2s, 1, 2, 3 CH2s, then a CH with a Br, and finally a CH3. And let's just count 1, 2, 3, 4, 5, 6 carbons. 1, 2, 3, 4, 5. 1, 2, 3, 4, 5, 6 carbons. I'm missing a CH2. 1, 2, 3, 4, 5, 6 carbons. Here it is. You see, it's very easy to make mistakes, so you have to count properly all of your carbons. So how many CH2 groups? Let's do it again. 1, 2, 3 CH2 groups. 1, 2, 3 CH2 groups. 1 CH group. There's a CH that it's not drawn here, attached to a bromine and then a methyl. Now, if that is changed from a primary to a secondary, this is now a secondary alkyl halides. If you recall, the rate is increased with the degree of substitution. Rate for E2 increases because we know that tertiary alkyl halide reacts faster than secondary than primary. This is for E2. This is exactly the opposite. This is reversed in the case or when compared to an SN2 reaction. Okay, so now there's something that we were doing earlier this morning, and I would like to practice a little more with all of you. And so here it's asking us to draw the major E2 product and to indicate the relationship between A and B. Okay, so first of all, we know that in order to draw the correct product, we need to set an antiperiplanar relationship between H and Br. And so we have to arrange our molecule. The way it is drawn now, it's not. And so we have a couple of options. You can either do it with a Newman projection first. So if we look down this way, what we have is something like this: ethyl, methyl, H. And then we have H, bromine on the left, phenyl on top. This is still not antiperiplanar, so we need to move this hydrogen and this bromine into an antiperiplanar relationship. So you have to rotate. And you can rotate both or only one. It's up to you. I'm going to keep constant the carbon on the back. So the bromine remains the same. And I'm just going to rotate the carbon in the front. And I need to put this hydrogen antiperiplanar to that. And so if we count clockwise to the hydrogen, there was a methyl, so methyl should go here, and ethyl should go here. And so then we can eliminate. We can put our base. This will go to form the pi bond, and this will get kicked out, and you would form something like this. We have an ethyl, we have a methyl, and in the carbon on the back, we have a phenyl, and we have an H. This is exactly the same as if you draw in the flat structure, carbon, double bond, carbon, and we have ethyl in the same side as phenyl, methyl in the same side as hydrogen. Okay, what about the other structure right here? And now, if you notice here, this arrangement is already antiperiplanar. But if we want to double check, let's do our Newman projection right here. So let's put ethyl on the top, methyl on the left, hydrogen on the right, and in the carbon on the back, we have bromine on the left, hydrogen on the right, phenyl down. And so these two groups are now antiperiplanar. So if we are going to eliminate, we don't have to rotate in this case. It's already done. So we can just eliminate, and we have an ethyl, a methyl, and the carbon in the front, and then we have hydrogen and phenyl in the carbon in the back. This is exactly the same as if we put carbon, double bond, carbon. I'm choosing the carbon in the front to be the one in the left. So methyl, ethyl is in the same side as hydrogen, and this is in the same side as phenyl. So as you can see, in one example, you get hydrogen next to a methyl. In the other example, you had hydrogen next to the ethyl. How do we call this? These are diastereomers. And you can assign, and you should be able to assign E and Z configuration. You just have to split and assign priorities. Split, assign priorities. This is priority number 1, and this is also priority number 1. This is Z in the same side, and this would be the E. Okay, so how about the question of what is the relationship between A and B, the starting materials? What did we change? Did we change anything in the carbon on the left? Let's label it as C1, just for purposes of C1 and C2. And if we want to assign stereochemistry, we can do that. And so the priority for this would be 1, 2, and 3. This is clockwise, and so this stereocenter is R. And let's see what happened here. The priority is 1, 2, 3. It's counterclockwise. However, hydrogen is in the front, so it looks like S, but it's in fact R. And so nothing has changed in that particular stereocenter. Now let's look at in the other side, and you can do it in your mind, or you can do it by assigning R or S configuration. I'm going to rotate this bond to place the phenyl going up. If I take this phenyl and I rotate it and rotate this sigma bond so that this phenyl is up, then bromine is going to be in the front and hydrogen is going to be in the back. And we notice that's the opposite absolute configuration as the one above. And so we kept one constant, R and R, but we only changed one. So that means that A and B are diastereomers. And notice that this A gave rise to the C isomer, whereas B gave rise to the E isomer of the alkene. And so this is exactly the meaning of a stereoselective reaction. E2 is stereoselective. One particular stereoisomer would give one isomer as preferential. Okay, so finally, or almost finally, this is a very important thing to practice. And this is what I left in the last pages of the lecture notes. And what I would like you to do is to draw all the possible products for an E2 elimination and indicate whether it's major, minor, or it's the sole product. First of all, let's see how many beta hydrogens do we have. We have one here, and we have two here. But because it's a substituted cyclohexane, we need to draw both chairs, locate the halide in the axial position because we know equatorial cannot eliminate, locate the beta hydrogens and see which ones are anti-periplanar, which are the only ones I can eliminate. And I'm giving you a tip, and I hope everyone can follow this because it's very easy to make mistakes. I just labeled these carbons arbitrarily, A, B, and C, and I made a note that I'm going counterclockwise in my numbering. This wedge lines, that means this is in the front. This goes to the front, or it's closer to us, closer to the viewer. And so this is a side view, or edge-on view of this planar structure, which can be considered a top view. So I urge everyone to please follow this this process. It's a four-step process to do that. And so first I start by putting my axial up, down, up. So those are the axials, and I only bother to do it in the carbons that I label as A, B, and C. So now the equatorial, if that axial goes up, the equatorial goes down. And because I'm saying that the chlorine is down, I'm going to put the chlorine right here. And this axial goes down, so that means this equatorial is going up, and this is where my methyl group is. And axial is also that ethyl group, which now they're all ethyl and methyl, they're both up, chlorine is down. Now this conformation cannot eliminate. So we have to do a chair flip. And the way to do that is you take this, bring it down, you take this and bring it down, and you take this and you bring it up. And you keep track of all of your the carbons. This corner right here is going to be this corner right here. This corner right here is going to be this corner right here. If you keep track of that, you will be successful, believe me. So okay, now we know that when we do a chair flip, everything that was equatorial now is axial, and vice versa. So we don't bother to do anything else. But if the chlorine was equatorial, now it's axial, and now this can eliminate. But let's see what happens with the rest. If our methyl, which was in carbon B, was equatorial, now it's going to be axial. If our ethyl was axial and was in carbon C, now it's going to be equatorial. And now let's check. Methyl and methyl are above; they're in the same plane. There's cis or syn, whereas the chloride is anti to both ethyl and methyl. So we did it correctly. Now let's identify the beta hydrogens that can eliminate. Is this hydrogen here? It's a beta hydrogen. This one right here, however, it's not anti-periplanar, and so it cannot eliminate. And the only option is going to be this one right here, in the carbon right here in front, next to the chlorine. And so we're going to have to draw a double bond right there. If we were to draw a transition state, we would have to put base, dotted lines here, and this will give rise to, I hope everyone was able to do this. And let's just stick to our naming. So B has methyl up. This will be B. This will be A. And this will be C. A has no chlorine, but we form a double bond between A and whatever the carbon was next to A. But it's not B, it's the other one. If we continue the letters, it would A, B, C, D, E, F. If you will, you can call it F. Doesn't matter, as long as you know that this is the product that you get. This is the correct structure. And is it the only one? Yes. This is the sole product. Why? Because once we have our chlorine in the axial position, there are no other possibilities that are anti-periplanar. Only one beta hydrogen that is anti-periplanar. So let's do one more. Now I'm asking here, I'm giving you Newman projections, and I'm asking to draw skeletal structures and the products for each E2 reaction. Draw the transition state and indicate the stereochemical relationship between A, B, and C. A, B, and C are these molecules that I'm drawing the Newman projection. And so one way to do it is, first of all, we need to decide, are hydrogen and bromine anti-periplanar? No, they're not. So we have to rotate. And I just want to do the easiest way. Sorry. I'm going to keep the carbon in the back. The green is in the front, and the purple's in the back. I'm going to keep the one in the back the same, constant. And I'm going to rotate so that bromine and hydrogen are anti-periplanar to each other. So if we go counterclockwise, bromine to the left has a methyl and then an ethyl. So now we can see bromine and hydrogen are antiperiplanar. If you want to draw the skeletal structure, then you do the zigzag in the plane, bromine H down, and then wedged and hashed line down, wedged and hashed line up. What is in this position here attached to the bromine would be the ethyl, and methyl would be in the back. Now, in the other carbon in the back, phenyl will be in the same side as the ethyl here, and on the back we would have the methyl. And the transition state would be something like this. The base pulls up that proton, that we're breaking that bond, we're forming a pi bond, and we're breaking that. We have a delta negative for, say, a t-butoxide base, and a delta negative for the bromide that is leaving. And so after that, then we can eliminate, and just for consistency, we keep the edge on view, and we fill in the blanks. Ethyl is in the front, phenyl is also in the front, and on the back we have methyl and methyl. That's a easy way to do it. Another way, or the second molecule rather, and let's just see what happened in terms of the stereochemical relationship between the two. The carbon on the back has hydrogen, phenyl, methyl, so nothing happened to the configuration on the carbon in the back, carbon 2. Just 1 second. However, carbon in the front, there was a change. And if you notice, we swap methyl and ethyl. The bromine stays in the same place, but methyl and ethyl swapped. And so we can immediately determine that A and B are diastereomers. We keep one stereogenic center constant, but we only change one. So that's immediately something we can recognize. Now, are these two antiperiplanar? No. So we have to rotate. And again, I'm going to keep the carbon on the back constant, phenyl, methyl, and then I want to put bromine antiperiplanar to the hydrogen. And if I go counterclockwise, left to the bromine, I had an ethyl and then a methyl. See how this switched in the Newman projection? We can also see that. And so this is a diastereomer. And the skeletal structure, again, you just do your zigzag, bromine, carbon, hydrogen in the same plane, and then we fill the blanks here. Wedge and dashed, lines down, wedge, dashed, lines going up. In the bromine, we swap the carbon with the bromine atom, we swap this substituent, so we end up with ethyl and methyl reversed as the other one. In the carbon that doesn't bear the bromine but has the hydrogen, we stick this to the same absolute configuration. And so we can see also from these two, they're diastereomers. Again, this would be the transition state. Dotted lines, we're breaking this sigma bond, we're forming a new pi bond, and we're breaking that sigma bond. Delta negative, because the bromide that is leaving, delta negative, usually an alkoxide base that we use. It's negatively charged. Now, after elimination, again, etch on to be consistent, methyl, double bond, carbon. What was in the front? Phenyl, just like the carbon above. It didn't change. However, the one, the carbon where the bromine was, it did change the configuration. And so now we have these two products are also diastereomers. And so at this point, I hope everyone is able to assign priorities. This will be priority 1, this will be priority 2, this will be priority 1, this will be priority 2. So this will be the E isomer. This on top, this will be priority 1, this will be priority 2, this will be priority 1, and this will be priority 2. The highest priority are on the same side, so this is the C isomer. And they're diastereomers, or geometrical isomers. Now let's look at the final example here. What happened to the, if we compare A, what happened to the carbon in the front? So we swapped methyl and ethyl. So we swapped one stereogenic center in the carbon in the front. In the carbon in the back, we also swapped phenyl and hydrogen. We swapped them up. And so we switched two stereogenic centers. Both were changed, so we can say that A and C are enantiomers. A and C are enantiomers. And so now, in order to eliminate, we need to put this in antiperiplanar fashion, and they're not. And so we have to rotate. I'm going to keep, as usual, the carbon in the back constant. I'll leave the hydrogen, phenyl, methyl here, and the carbon in the front. I'll rotate so that the bromine is antiperiplanar with the hydrogen that I'm trying to eliminate. So bromine, going counterclockwise or to the left, was an ethyl group, and then a methyl group. Now you want to translate into a skeletal structure. Now notice how this is going to be different from the one above, because we're basically rotating sideways. And so now we have a methyl, and down we have a phenyl. Now we need to fill in the blanks. So on the back is the bromine, on the front is the ethyl, on the plane is the methyl group, and down also in the plane. So in other words, methyl and phenyl are also antiperiplanar to each other. That's not something we care about, but this is what the Newman projection is telling me. But it's also telling me that bromine and hydrogen are antiperiplanar. And so in the carbon 2, which is the carbon on the back, if you want to label it that way, and this will be carbon 1, so this will be 1 and 2. On the front, we have a hydrogen, and on the back, we have a methyl group. Now notice here that bromine and hydrogen, even though we don't have them in a zigzag orientation, this is just a representation. We know that they're also antiperiplanar. And we can see that in our Newman projection. And so you're able to also set up your reagent, your alkyl halide, in a conformation in which your H and the Br atom or your halogen atom are also antiperiplanar, and they do not necessarily have to be in the same plane like I've done in the past with the zigzag. For me, it's easier, the option above, but you might encounter this, and so I wanted to give you that example. Now, if you eliminate, if you have t-butoxide as base or DBU, something like that, a strong base, you would form a pi bond, you kick out the bromide, and now what is the alkene that we're going to form? That's the question, and this is where confusion can be created, and this is where I would urge all of you to look at your Newman projection. We're going to be removing H and bromine, and so just stick to your Newman projection. Ethyl and phenyl are going to be on the same side, so just arbitrarily I selected the bottom, ethyl and phenyl, and in the other side we're going to have two methyls, methyl and methyl. And so you can see this is also the Z isomer that also was formed from the enantiomer. So two enantiomers give rise to the same diastereomer, the C isomer in this particular case. But it is important that you recognize that A and B, two diastereomers, give rise to two different diastereomers. This is the crux of why E2 reactions are stereoselective. One stereoisomer will give one stereoisomer preferentially. In this case, compound A or B or C, which are enantiomers, give the Z isomer, and compound B, which is a diastereomer of A and C, give us the E isomer. All right, I hope that this will be useful for everyone, and thank you for watching.